We are starting now section 5.6. This is the first section in the Calculus 2 class, and this is continuing what was discussed in the previous section of material. We're going to talk about the u substitution, but with definite integrals, and we're also going to talk about area between curves. I have this theorem here, which is substitution with definite integrals, and I'm going to show you two examples in just a minute to tell why this theorem is very useful and very handy. But I'm going to come back to that. What I want to point out real quick is this theorem 8, and it has to do with functions that exhibit some symmetry. If a function is even, that means it's symmetric with respect to the y-axis, and that's this first picture here. It says if a function is even, if you're looking for the integral between negative a and a, it's just going to be twice the integral between 0 and a because of that symmetry. Similarly, when we have functions that are odd, that means they're symmetric with respect to the origin. If you're looking at the integral between negative a and a, in this case, it's going to be 0 because the areas between the curve and the x-axis are going to cancel each other out. So if you remember, if the area between the curve is above the x-axis, it's going to be positive, below the x-axis is negative. Because of the symmetry here, we've got these same areas, but one on top and one below the x-axis. Same thing here with the kind of pink colored areas. So they kind of wipe each other out, and you end up with just a 0 there as the sum total. We will revisit this idea later in this section, but for now I want to refocus on Theorem 7, which has to do with u substitution with definite integrals. And the thing that's really important here is if you look at the upper and lower bounds, instead of it just being a and b, it's going to be g of a and g of b. This actually saves us some steps, because what we're going to do is once we define u, and in this case u is g of x, we're going to redefine the upper and lower bounds based on that. It actually saves a few steps when you're working the problems. I'm going to go to the bottom of the page and work the first two examples. The first one I'm going to work without using that. The second one, I will use that. So we have the integral from 0 to 1 of t cubed times 1 plus t to the 4th, that whole quantity cubed, dt. In this instance, I'm going to let u equal 1 plus t to the 4th. And du will then be 4t cubed dt. So if I look at the integral that I'm given, I have the t cubed and the dt. I'm missing the 4, but I can create that. If I put a 4 inside the integral, I can put a 1/4 on the outside. So in other words, I could have this. Now I can do my u substitution. U is 1 plus t to the 4th, so I'll have u to the 3rd power, and then the 4t cubed dt just becomes du. Now I need to make a distinction here. These upper and lower bounds are reflecting t values, not u values. With the theorem at the top of the page, We could change these bounds to reflect the u values. I'm showing you that you can still work the problem without doing that. It just takes a few extra steps. So I want to show you the usefulness of that theorem. So when I integrate u to the third power, I'm going to get u to the fourth power over 4. That's kind of an ugly looking 4. Let's see if we can clean that up a little bit. There we go. And again, we're evaluating not from u equals 0 to u equals 1, but t is 0 to t equals 1. So what I then need to do is go back and instead of the u, write 1 plus t to the fourth. While I'm doing that, I'm going to take this denominator 4 and bring it out with the 1/4. So I'm going to have 1/16. Then it's going to be 1 plus t to the fourth raised to the fourth power. And we're looking at that from 0 to 1. When t equals 1, t to the fourth will also be 1. 1 plus 1 is 2. And then 2 to the fourth power is 16. Now, I'm going to plug in 0 for t. 0 to the fourth is still 0, so I have 1 plus 0 inside the parentheses. That's 1. 1 to the fourth power is still 1. 16 minus 1 is 15, so I get 15/16. Now, what the Theorem 7 says is that instead of having to write the t equals 0 and t equals 1 and then go back and resubstitute for t, what I can do is go ahead and change the upper and lower bounds of my integral to reflect the u values. That's what I'm going to do with the second example here. It just saves a couple steps. In the second example, I'm looking at the integral from 0 to 2 pi of cosine z over the square root of 4 plus 3 sine z dz. In this case, I'm going to let u equal what's inside of the radical. So u will be 4 plus 3 sine z. Oops. And then if I look at du, it's going to be 3 cosine z dz. So in the integral that I was originally given, I'm missing that 3 inside of it. But again, we can create that. If we put a 3 here, I just put a 1/3 in front. So go ahead and rewrite all of that. So now I have u inside the radical, du, 3 cosine c dz. I am good to go. So I can go ahead and do my u substitution, but in this case, I'm going to also change my upper and lower bounds. If z is 0, sine of 0 is still 0. 3 times 0, 0. So we have 4 plus 0, or 4. Then I look at 2 pi. Sine of 2 pi, well, that's 0 as well. 3 times 0, still 0. 4 plus 0 is 4. And I end up with 1 over the square root of u du. But in a sense, this doesn't matter because I'm integrating and my upper and lower bounds are the exact same number. And if you remember, when the upper and lower bounds are exactly the same, I end up with a 0. Technically, it's 1/3 times 0, but it's still going to be 0. And that's what Theorem 7 gives us, is it's going to tell us when we do our u substitution that we can also go ahead and change those upper and lower bounds to reflect that u substitution. In the next video, we're going to do 2 more examples of this.